rule says 5% or under works. Quadratic's done. No way that you have to do the quadratic. You walk right around it. Also tells us the initial problem that our H3O concentration is 9.35 times 10 minus 30. They may ask you, one other part of this question is, you found the hydronium ion concentration. They may ask you, what's the pH of the solution? You have it right here. Knowing that's to the minus third tells me that the pH should come out somewhere around 3. Pretty high, it comes out 203. And that's your pH of that solution. But again, had you gotten to that point and found that you had, say, 6 or 7% there, you're stuck. You have to go back and do the quadratic. A lot of times, though, the assumption works. Always give it a shot. It's always working. Because most of these Ka values you'll see on that table are very small. It's always worth a shot to take a look. Because if you can do this much math versus going into the quadratic, absolutely worth your time. Just to do the quick validation, see if it works. Come back about 20 after. Take a 10-minute break, come back a little more. Write the generic reaction. HA plus water goes to plus minus initial change equilibrium. They told us we started out with 0.175. The tricky part here is this H3O plus is after it reacted, after all of it started to break apart. This number here, stripping all of this, ends up here at the equilibrium. Down here. We assume that neither of those was present when we started. And we have enough there to fill the table out. If there was none of this here, and now we have this amount, this side has to be plus 5.62 10 to the minus 4th. Same change for this one. Same concentration for this one. The only one we have to do any calculating with is the HA. We know how much we started with. Now we know how much we lost. The number that we end up putting in there is so now we have everything in equilibrium. If we know all the values at equilibrium, we can find Ka. Remember that Ka equals this guy, over that one. But we have all the numbers now. We just have to put the numbers in that we just calculated. I've placed in the numbers that we found. The Ka for this one is 1.81 times 10 minus 6. It's a different problem where they tell us where we started, where we ended, and they ask us to find the Ka value for that acid. Again, the hardest problem that you run into is the one where you end up using the quadratic. This one is also challenging. Just remember, they tell you where you started, they tell you where you ended. You have to find out, fill in the answers. Very much like we did in the lab last week. You knew this one, actually you knew this one, you found the change in between. You find the K. The lab you're going to do next week, I think we're going to do the K determination of weak acid. Do essentially the same type of problem.
Oh boy.
This problem here, one thing that we talked about the 5% rule. There's another concept, percent ionization. Sometimes we want to know just a numerical number of how much does it break apart? How much of the acid actually breaks apart? The percent ionization is really a look at the 5% rule. Percent ionization equals the concentration of the ionized acid over the concentration of the initial acid. Times 100%. It's just like doing the 5% rule, but really what you're doing now is you're doing it with the answer that you just got. For example, do this problem right here. Percent ionization, concentration of the ionized is what you got out of your ice table. That is your 5.62, 10 to the minus 4. That's how much of an ionized. How much ionized you can also look at as the H3O plus amount. The total amount is 0.175. That's 100%. The reason we calculate this, it just gives us a feeling for how much of the acid actually broke apart. This calculation here comes out to be 0.321%. Tells you that not even a third of that percent of that acid ever broke apart. Very little of it. The 5% rule is really a measure of that, but we can also call it percent ionization. That acid, very little that broke apart. You can also see that third of a percent breaks apart. That means most of it stays bound together. We see that in the ice table, most of that staying unbound. You also see it reflected in the Ka value that you got. It's exceptionally small. Your book does a discussion on mixtures of acids, and we're not going to cover that. Mixtures of acids is not covered. Starts on page 717 and goes through to 7, ends on 719. We are not doing mixtures of acids. I don't have time to worry about those. Where we'll pick up is, the book almost divides it in half, is everything we've talked about here has been acids. Now we have to look at the base side. And the problems are very much the same. You have to go back to looking at our bases and see strong versus weak again. As it turns out, you look at bases, we have strong, and we have weak. Strong ones, what do? They break apart completely, 100% ionization. There's a short list of those that we're going to worry about. Lithium hydroxide, sodium hydroxide, potassium hydroxide, strontium hydroxide, calcium hydroxide, barium hydroxide. These are all our strong bases. They will dissociate completely in water and give you all the OH they have. The weak list is much longer. Commonly, NH3, CH3NH3, and there's tons more of those. But because they're weak, they're going to have an equilibrium constant assigned to them. There's Ka for the acids. The equilibrium constants now for these guys are K sub B. Everything that we talked about Ka applies to Kb. It's a measure of their strength of the base. It's just the analogous term of using a base instead of an acid. If we look at two problems with these, we'll look at 1511. Here we have, find the hydroxide ion and, sorry, OH minus concentration, hydroxide ion concentration, and the pH for a 0.01 molar barium hydroxide solution. First thing comes to doing these problems, you have to recognize that it's on the short list for the strong bases. That's key, because there's going to be no KB. Again, if you try to look up a KB for it, it's not going to be there, so that's the other thing that you notice. But you have to realize that barium hydroxide, when it breaks apart, gives us two hydroxides out of the reaction. So when we use it, when we look at its strength, that means the molarity of this acid or base when it breaks down, the molarity of the hydroxide is going to be 0.02 molar. So you get two hydroxides out for every one of this formula molecule that you're starting with. So we know how much you gave, gives you 2 for 1. To find the, we found this part, OH minus concentration, that was easy. Next thing we want to do, might as well find the POH. The POH for this is 1.69. But they don't want the POH, they want to know its pH, because everything goes back to pH, something we can actually measure. Don't forget, pH plus POH has to equal 14. So if I know the pH of this, pH plus 0.69 equals 14. Subtract it, you get a pH of 12.31. The only extra step in these problems is by default you end up finding the OH minus the POH. To get to the pH, you need this expression. You need that part to get the extra, to get from one to the other. Again, if it's a strong base, use it directly. If you have a weak base, there is a table of KBs. Let's look at a problem 1512, and you have a weak base. This is a weak base problem. We're going to set it up a lot like we set up the acid problem. We're going to work through the same parts. Let's see what we have. We have a 0.33 molar concentration methylamine. And we want to find the OH minus. We want to find the pH. Methylamine is this. So the first thing we have to do, just like when it was the weak acid problem, we have to write some type of reaction to show what's going on. It's a base reaction. CH3, NH2, always reacts with water. Remember that because we're dealing with a base, one of the products has to be hydroxide. So one of the products over here is OH minus. And if I steal a hydrogen off the OH, it has to be transferred over to CH3. This becomes CH3, NH3.